I show here the heavy element enrichment within damped Lyman Alpha Systems as measured across most of the cosmic time. So the x-axis is redshift, y-axis is an estimate of the metallicity from absorption lines, again, comparing the metal column densities with the hydrogen column densities that we've discussed. And you'll notice there's no upper limits on the chart. So every region in the universe that shows this 2 times 10 to the 20 column density of hydrogen gas also shows some trace amount of heavy elements. The metallicities do go down to nearly 1,000th of solar, but there's no pocket in the universe that appears unenriched at these column densities. And so that obviously associates, well, given that heavy elements, we believe, or I should say no, are generated in stars, that obviously associates the gas to galaxies and either current or previous star formation. Another line of evidence comes from what we call the so-called fundamental plane of DLAs. This is now a 3-dimensional plot of redshift and metallicity, which I just showed you. In the 3rd dimension here is velocity width, so the dynamics of the gas, again associated with the metals, not the hydrogen, because as you've seen, the damped Lyman alpha profile shows nothing about kinematics. It's all about the Lorentzian. Nevertheless, the data here lie more along a plane than some random population, and we've inferred that as indication of a mass-metallicity relationship. And in fact, when you look at the distribution and the normalization, it's remarkably well similar to what we observe in galaxies at the same redshift. There are indications from simulations as well. I showed this plot previously, and previously I emphasized the optically thick gas. The gas may be around this color, but note the gas around yellow and red. Those are the column densities associated with DLAs. And in numerical simulations, you find that that gas is mainly within the galaxies, the regions that are forming the stars within the simulation. That's one snapshot. And here's another snapshot from a repo. The gas distributions can be quite complex, but again, at the column densities of DLAs, you in these simulations associate them with quite closely to the star-forming regions, or aka the galaxies. So, with that, those inferences in mind, I want to highlight how hard it's been, and continues to be really, to find direct links between this gas and galaxies. So a couple slides on that. Again, we're on this portion of the frequency distribution, the very highest end, the DLAs. Efforts to directly image the gas have been largely unsuccessful. So deep broadband imaging to use the so-called Lyman break technique and identify galaxies that are bright, and a bit faint because of the IGM in the 3 colors have largely not identified candidates that you would call galaxies associated with the DLAs, possibly because they're too faint, possibly because they're too close to this bright background quasar, which makes it difficult to find faint little blobs nearby on scales, say, of 10 kiloparsecs. So other techniques have been employed, some with varying degrees of success, perhaps the way to say it. One approach is to do what I would call a clever imaging of these systems, and here we're actually nicely using some of the techniques we've described this week. Identify sightlines towards a quasar, towards quasars that have both a damped Lyman alpha system, that's this strong absorption feature you recognize here, and additionally an optically thick blob of gas, a Lyman limit system, which cuts off the light from the quasar at its Lyman limit, by definition, and enables one to image the galaxy in this spectral region, okay, where there's no quasar light whatsoever because it's been completely absorbed by this higher redshift optically thick gas. Up here you're seeing the transmission curves, and so a U-band, they're kind of upside down. One is here for transmission, so high transmission of the U-band. So you've got a U-band filter covering this spectral region to image for the galaxy without any of the quasar light. And indeed it works quite nicely. Can we turn on the lights for this presentation? Now that I'm in slide mode, thanks. I guess it's mainly the sunlight, can't turn that down. Quasar, go to the U-band, no quasar, and you can look very sensitively for emission associated with the galaxy on even the smallest of scales right underneath the quasar. So that's been tried. Again, another example, quasar in the R-band images, no quasar in the U-band images, and you can look very sensitively for the emission, even on all the way down to scales of 0 kiloparsecs. As an aside, it's tough to do the analysis actually on larger scales because of the number of background sources. And the bottom line is this is a stack of all the data, say about 30 damped Lyman Alpha systems with this technique. There's not much of anything there. And so you place upper limits on the star formation rates. This is the star formation rate surface density in solar masses per square kiloparsecs of even as low as 1/100th of a solar mass per square kiloparsec, which in hindsight is not so surprising. Given the column densities we're talking about, if you just adopt the standard Kennicutt-Schmidt law, as we call it, you wouldn't have expected very high star formations right at that location. But in addition, we're not finding bright counterparts, luminous counterparts, anywhere within that roughly 20 kiloparsec search radius that we can do very sensitively. And it implies that the typical star formation rates of these galaxies are less than a solar mass per year. Another approach has been to randomly place spectroscopic slits onto the quasar and hope that something appears within one of the slits. It's very sensitive to Lyman Alpha emission and also near IR emission within a search radius of about a few arc seconds. Obviously, once you go away from the quasar, this multi-slit thing, there's lots of gaps where a galaxy could hide. There's been some successes. Johan Finbo's really pioneered this work. This is a detection. This 2D image is not very exciting, but the O3 is cleanly detected an emission of the galaxy counterpart to the damped Lyman Alpha system, and shows this, in this case, a star formation rate of several tens of solar masses per year. Though that's why they haven't really published a complete census of their experiment to show how frequently they have detections, but there are at least some. One can then, of course, use an IFU that avoids this, multiply slit aspect. But thus far, the best IFUs have been the near-infrared, where the sensitivity is a bit poor. But again, some successes. Here's a H-alpha emission from a galaxy counterpart, again, to a DLA. Here, I think at around a redshift of 2. A few successes, but by and large, maybe only 20% of the time is there an obvious counterpart within these data sets. Probably, I believe, associated with a limited sensitivity. We're undoubtedly going to see more efforts with this in the optical, using MUSE and eventually KCWI. I'm particularly excited by this, actually going and imaging the gas directly. We have 2 projects going on with ALMA. One is to target CO emission in the kind of redshift less than 1 universe. Here's a quasar where there's a foreground damped Lyman Alpha system, and here's a whopping CO detection. And of course, with ALMA, you can both detect the gas and resolve its velocity field if you have enough spatial resolution. This is showing the clear rotation curve of a galaxy here at a redshift of only 0.1. It's not very distant damped Lyman Alpha system, but nevertheless showing that the technique is successful. And we've got other positive detections already from cycle 2 in ALMA. And with a sensitivity of order about 1 billion solar masses in molecular gas. And then most recently unpublished even at redshift 4, looking for the 158 micron emission from carbon plus. Here are the quasars, each which shows a DLA not shown, and now C plus detections at high statistical significance at a redshift of 4. Velocity fields, this one at least indicating some rotation. This is a whopping galaxy. Star formation rate implied from the continuum of, I think, 50 solar masses per year. The rotation curve is hundreds of kilometers per second. And remarkably offset by almost 30 kiloparsecs. We were seeing H1 gas at very high surface density, 30 kiloparsecs away from the main star-forming region of this redshift 4 galaxy. And I have to admit, don't fully understand it, but these are early days for the technique. So stay tuned for a number of these techniques going forward. I think the connection between galaxies and this hydrogen gas will become much more clear in the next, say, about 5 years. Any questions on associating DLAs to galaxies, or DLAs in general? Get rid of that. The last thing I had in the notes are just a couple of figures on the identification and analysis of this hydrogen gas, hydrogen absorption and gamma ray burst afterglows. The upshot of this story is that the absorption is extreme. It's as extreme as it gets, I'd say, in the universe. Here's one example, kind of an extreme example as well. But the damping wings here, okay, obviously, right at the GRB afterglow redshift. So this is gas in the ISM of the galaxy where a gamma ray burst exploded, small star-forming galaxy in the distant universe. And the column density here is nearly 10 to the 23 particles per square centimeter. Remarkable. These are, as I said, are the highest H1 absorptions that I think we'll ever detect. That's a bit strong. Certainly have detected so far. And that's characteristic of the sample as a whole. So this is quite complementary to the quasar technique, where with quasars you randomly observe hydrogen column densities throughout the universe. Here, the light source is a massive star that has exploded, so it occurs within some star-forming region of a distant galaxy, and you get a snapshot of the ISM on the scale within that galaxy on these scales. Quite complementary and quite nice. All right, that ends the DLA lecture. All right, so for 4 days, we've worked hard to go through or introduce yourself really to the concepts of H1 absorption. Let me pause here and give ourselves a bit of a recap, or as I like to describe it, list what I hope you learned this week. More likely it's what I hope you will learn from the notes when you have a time to really digest it and think about it and come to grips with it, all the material that I've thrown at you. What I would hope is that you've got now some understanding of the key physics of the Lyman series and continuum opacities. We went through that in some gory detail. Several techniques to characterize the Lyman alpha forest, this frequency distribution that I've harped on quite a bit. The fluctuating Gunn-Peterson approximation, which I will re-emphasize as we go forward here. I also put in the notes, but didn't have time to discuss the concept of the gene collapse by Job Schei for a description of the IGM, or the clouds, Lyman alpha absorption clouds. Some modern constraints on the incidence and evolution of H1 absorption. We went through that quite clearly in its many opacities. The principal measures of optically thick gas, and now the DLAs, which I just completed. And I've provided you, hopefully, with techniques to generate and analyze your own IGM. So that's quite a bit, obviously, and I've tried to go through that probably a bit too quickly. But what I would hope that most of all what you've learned, or where you are compared to where you were a week ago, is that you could go to the literature now and critically analyze papers on the modern research of H1 absorption, where maybe a week ago it would have been a bit daunting to open one of those up and read about Lyman limit systems and fluctuating Gunn-Peterson approximation and aspects like that. So I'm hopeful you've taken a big step forward on that. In fact, I'd like to poll the audience and see if you believe that you have. So get out your cell phones and raise your pen. So do you feel you now can critically analyze the literature? Receiving your responses. How does this work again, Mark? Mark here? Oh, yeah, that's right. Mine doesn't flip. I guess that's the problem here. Well, I think they've been downloaded to my laptop. So let me see the results of the survey. Got a few yeses. All right, that's not so bad, I guess. Curling, really? This audience, yeah, something about this audience. Not sure why curling was favored over skiing, but it seems that was the case in this audience. It's a bit odd. I think you all might want to go on one of these astronomy cruises and do some shuffleboarding then. I hear that's very exciting. All right, so actually you're about to be tested on your ability to critically analyze, because now, for the remainder really of my lectures, I'm going to go through modern analyses of the intergalactic medium, or H1 absorption, and discuss as well some future approaches that we'll be taking. And hopefully this makes sense to you, and whereas a week ago it may not have made any. At the heart of it all, or at least of a lot of the research, is the cosmic web paradigm. So the notion that the gas is distributed in filaments on the largest of scales. This is a prediction of our modern cosmology. It's really a prediction of any simulation of the early universe. I show three visualizations of gas on the largest of scales. And it's truly become the modern paradigm for the way the diffuse gas is distributed. So I've been somewhat fast and loose in what I've called the intergalactic medium so far this week. Let me now tighten up that definition. For me, truly, when I say IGM, I am referring to diffuse gas that is in between galaxies, so intergalactic medium. Not the gas within galaxies, not even the gas really around galaxies, but between galaxies, so IGM. And it's that material which is distributed in these filamentary structures on the largest scales. It's in a quasi-linear, it's not too far from the mean overdensity, so kind of quasi-linear regime. And the key of what's a lot of the research that's going on these days is to leverage this paradigm to constrain both cosmology as well as the IGM itself. So having a well-founded model enables us to do really tight, high-precision measurements of both cosmology and this IGM. And in fact, quite a few of the results that I'll show you do demand these simulations, which should make you a little queasy, perhaps, because it's hard to simulate the universe. But I'll say a few more words about that in a moment. To remind you about the fluctuating Gunn-Peterson concept, I went through this a bit quickly when I introduced it. It's that notion that the opacity in this IGM is associated with some physical quantities, which we bury in this A. But more importantly, the overdensity of the gas, or of the region of the universe, as you would measure from the dark matter field. So again, going through a visualization of that, in this middle panel, we've got both plotted the overdensity, which is the dashed line, or the dotted line, and the temperature of the gas, which is the solid line. And within this hydrodynamic simulation, the prediction appears of the transmitted flux. The black is without accounting for the Doppler broadening and the Hubble broadening. The dashed line is what you would actually observe. And so you can see quite clearly the connection between high overdensity and low flux, or high opacity, high overdensity, high absorption, which you would expect intuitively. And that's what's encoded in this description of the fluctuating Gunn-Peterson approximation. And to remind you where the 1 plus delta to the squared comes from, all right, I'm sorry I turned down the lights. Well, it looks like the sun's helping me out enough you can see this. But tau is equal to, thank you, fundamental constants times the number density of hydrogen atoms and some length scale. And this number density of hydrogen atoms can be inferred from ionization balance or ionization equilibrium, the number of electrons available, number of protons, and a recombination coefficient. So the hydrogen atoms goes like the product of two densities. That's the 1 plus overdensity term squared. And this, as I'll go through again in a few minutes, comes from a temperature density relation that is also predicted from both hydrodynamics really, some power law of the overdensity for the temperature. Okay, so the two from the particle densities of electrons and protons, and the rest of that from the temperature of this intergalactic medium. To impress upon you that it's not ridiculous to think one can generate simulations of this intergalactic medium at very high precision, I show you a snapshot of a simulated spectrum and a snapshot of a real spectrum of the IGM. Okay, which one is which? Now that you're experts. Anyone willing to take a stab? It's not so easy, is it? The bottom is which? The bottom is Keck. I don't think so. And to be honest, I don't even know for sure myself. But I'm pretty sure that this is real. This very narrow feature here, when I see a very narrow one there as well, I'm pretty confident everything here is at high solenoid, so real. And that is really narrow, as in too narrow to be hydrogen. So I think that's a metal feature, whereas the simulation has no metals in it. So I think that's the real data, and that's the simulated. Okay? But very hard to tell. So visually, I think you'll agree there's some hope you can simulate this intergalactic medium from first principles to high precision. Indeed, all the required astrophysics is in place, really, for these simulations. Maybe, can I turn the lights down again? Thanks, sorry. And that is unless our understanding of the IGM is completely off, and maybe magnetic fields and blazars really do matter. But as we are today, we believe we have all the hydrodynamics that's necessary to model this gas on these large scales. Right? We're not talking about galaxies here. We're talking about tens and hundreds of megaparsecs. The real unknowns are the radiation sources and when they shined and for how long they shined, and those aspects, which are unknowns. And indeed, what a lot of the effort is these days is trying to resolve that history by looking at some of the implications or imprints on the intergalactic medium. We also, at some level, need precise cosmological parameters, but they're somewhat secondary. So there really is reason to believe you can predict the IGM from first principles today, or tomorrow at least, in cosmological simulations. And just to poke an eye at all the Lyman Alpha mission we've been hearing this week, I think the chances of doing that from first principles, good luck to you. We are still in this stage of descriptions of what's going on. We have some blobs of gas and photons rattling around with them and shells and so forth. It's my own work. I'm not trying to cast stones at anyone else but myself here, but that's a very hard problem, all right? Simulating a galaxy from first principles, its interstellar medium, the star-forming regions, how the dust gets there and how the photons get out. Challenging. Okay, so some slides on cosmology. Keynote decided to stop letting me put Greek letters in it, so bear with me a bit on this. Apparently it's a well-known bug of Keynote. How nice. They didn't tell me about that. So most of the constraints we get on dark energy or omega baryon, actually not omega baryon, some the other, do require these models, and do require for sure our paradigm of this fluctuating Gunn-Peterson approximation of the intergalactic medium. Let me start with big omega B here, the mass density in baryons. That's actually stems directly from theories of the Big Bang nucleosynthesis, how the light elements were generated in the early universe. That's a well-developed theory based primarily on equations of nuclear state, nuclear transitions. Doesn't require too much about cosmology other than that the universe was expanding and cooling. And so we have now very precise predictions for how much light elements will be produced as a function of just a few parameters. This is showing the production of deuterium here normalized to hydrogen as a function of time. If you can't read it in the back, that's 100 seconds. So just about a minute, a few minutes, and you see the buildup of deuterium as the universe is cooling to temperature, 60 kV, whatever that is, and then the freeze out of deuterium as you go to a few thousands of seconds. And here are the dependencies that are being shown as how many effective neutrino species there are, or light relativistic species there are in the universe. Now, on the right here, I'm plotting the abundance of light elements, deuterium is what I'm going to focus on, and its sensitivity to eta, which is the ratio of the matter baryons to the density in photons, which we've measured precisely. And you see an order of magnitude, this is magnitudes here, the back, from the minus 3 to the minus 4. It's an order of magnitude variation, order of magnitude, eta parameters of linear relationship between deuterium and most sensitive light elements to this omega baryon quantity. And the game has been to use measuring galactic medium to nail down this deuterium ratio. And I'll show you some examples now. Also, by the way, jump in anytime on these slides. Happy to take questions on that. So the approach is using what we've now learned about hydrogen absorption lines but we can go using both isotopes, first dose of hydrogen. Here's an example of deuterium absorption in a wing of hydrogen alpha line. The predicted ratio being the synthesis is of order 10⁻⁵ deuterium particles per hydrogen particle per proton. And therefore you're going to require order 10 to the 17 hydrogen atoms or more in order to detect deuterium even in the strongest line alpha, which is shown here. As we calculated at the start of the week, the energy levels on the reduced mass, since we have a neutron now in our nucleus, that leads to an 82 kilometers per second shift to the blue, higher energy for deuterium. That's 82 kilometers per second, so trust me. And you see this little slip here of absorption for deuterium out here in the wing. In order for the hydrogen not to swamp the absorption of the deuterium, you need a B value that's of order 20 kilometers per second for this very strong Lyman alpha line. Actually, it would be nice, I guess. Maybe I'll put in a notebook to show that once you're up to about 30 kilometers per second, this thing will be swamped by just the alpha rod plus the strong absorption. So that was the original approach, was to identify regions of the universe that were low in metallicity, near primordial. I should have mentioned this. Deuterium has destroyed the stars, so if you have a system where there's been a lot of enrichment or a lot of processing, nuclear processing, then the deuterium ratio goes down. The deuterium is destroyed. That's what we observe in our own Milky Way, for example. So you find, the game here is to find nearly primordial, it's just about impossible to find truly primordial, regions of the universe that have this weak, have enough hydrogen to detect the deuterium, but have very narrow lines so that you have the chance to do this analysis and so on and so forth. It's hard to find such systems, still is very hard to find such systems, but Tytler and his collaborators had some successes as soon as Keck turned on. This was in the early days. You measure the hydrogen from our continuum opacity, which you've learned about, get a precise measure of the hydrogen column density, and you measure the column density deuterium from the Lyman alpha line here. So that was done. Placed a nice constraint in the early days. This approach was somewhat limited because these systems are quite rare. Because the deuterium is weak and often blended with the intergalactic medium. I'll remind you, we still have on top of all this absorption the random stochastic opacity of the intergalactic medium. So a number of the lines that were originally identified as deuterium lines have now been appreciated to be unrelated to deuterium, but intergalactic medium. And it's also limiting that we have a single line for deuterium to analyze. It makes it even more susceptible, right, to this IGM blending. So the approach, okay, there's the hydrogen from that decrement at the Lyman limit. The approach these days then is to forego Lyman alpha in terms of the hydrogen and the deuterium. Instead, look for systems that are damped in the hydrogen line, so you get the column density precisely from the damping wings, as we've learned. And now look down into the Lyman series to see the deuterium absorption here at 82 kilometers per second from 0, which is the hydrogen without the neutron. Here's the deuterium, 82 kilometers per second. You see a series, the Lyman series absorption of the deuterium line, and now you have multiple lines to gain confidence and precision in its measurement. It's still difficult to find these kind of rare systems that the hydrogen that you don't have random hydrogen lines killing you at the deuterium, but they exist. And this is even a bit more precise of a technique than the one that was applied in the early days with Lyman limit systems. Here's the state of the art from Ryan Cook's paper in 2014. Measurements of deuterium to hydrogen from the intergalactic medium, the blue dots plus his new red dot. These are the most precise measurements. There are additional ones not plotted here, which are just not as precise and not included. And the green bands, from deuterium, as I showed you a few slides ago, you can directly map to the mass density in baryons, omega baryon. And you may be aware that the cosmic microwave background also gives you an approach to estimate that quantity from mainly from the height of the second peak in the decomposition of the power spectrum relative to the first peak. I could go on more on that, but I won't. So there's the green. The estimate from the CMB is in green here, and you can agree by eyeball that those are in astonishingly good agreement. And you can use the two techniques even to place more precise constraints on this effective number of relativistic species, and then there's your combined constraint on the mass density of baryons. When I talk in a crowd, even to a public crowd about this, I emphasize, and I will for you as well, this is measurement of the same quantity, megabaryon, in two completely different data sets, right? IGM spectroscopy versus the CMB, at two very different epochs, based on two very different theories, BBN versus the CMB processing, each with their own systematics, right? Each with their own teams, blah, blah, blah. And the agreement here is astonishing. It's perfect. That's really a triumph of science when you can measure the same quantity, that precision, with that different of a technique and get the same answer. So I consider the strongest scientific triumph that I've witnessed in my days of astrophysics. Anywho, we're now at the level that any disagreement that does arise between the two techniques will holler, quite likely, new physics either within the paradigm of BBN or within the CMB. And going forward, that's going to be the name of the game. One can improve the precision on the BBN side. Actually, the biggest source of uncertainty today is in some of the cross sections in these nuclear calculations, and they're being measured now in the lab experimentally. So there's progress there to come. Any questions on using hydrogen absorption for a megabaryon? Please. Yeah, so the question is, by the fact that we're limited to narrow and presumably rather cool or cold, at least quiescent gas in the universe, does that bias the deuterium? I can't see how. The biggest concern really would be astration, that the deuterium has been destroyed in stars. And I can't see why a cool gas would be more likely. It would be enriched gas that would make me, give me the greatest pause, and we know to avoid that. Any other questions on megabaryon? Okay, so hopefully you understood that now that you have an expert knowledge of absorption lines. Let me say a few words on the matter power spectrum. This is the power spectrum of our universe on scales of about 10 megaparsecs, a few megaparsecs to 10 co-moving megaparsecs. And I'll introduce you to the concept and just show you some of the measurements that exist today. So again, the fluctuating Gunn-Peterson approximation links overdensities to optical depths. We measure fluxes, so we measure e to the minus tau in the data, which is yet another transformation of the overdensity, and a pretty ugly one at that. It restricts the dynamic range that we're sensitive to quite severely, but it's what we've got. As I'll mention in a moment, with this, I'll say it in words, but then show you, the Gaussianization of this preserves the overdensity rank ordering, at least we believe it does, which then allows us, by measuring spatial correlations in the flux. So now visualize a spectrum, and I've got undulating flux, undulating opacity, and hence undulating overdensities. I can, with a fast Fourier, or with a Fourier transform, measure the spatial correlations of those overdensities on the scale of that spectrum, which is spanning roughly 100 megaparsecs. Okay, so that's the approach qualitatively. It starts with the so-called probability distribution function PDF of the flux field. So here's a simulated a long time ago, spectrum of the IGM from a numerical simulation. So normalized flux and absorption lines. The PDF is just very simply the distribution of those fluxes, those normalized fluxes. So we've got largely unabsorbed gas here at the high flux end, right, and highly absorbed gas at the low flux end. This flux PDF I'll show you a few times. It'll be used for several different aspects of examining cosmology in the IGM. But it's just a PDF, right, of these flux values, nothing too exciting. The underlying assumption is that this PDF is a description of the tau field of the optical depths, which in turn is a distribution of the overdensities. It's been tested extensively with simulations, so that gives us some confidence in what goes forward. The Gaussianization of the flux field, it's a mouthful, is to map this, which is the observation, or becomes the observation, right, the flux PDF, onto this, which is the Gaussian field we believe exists for in our cosmological paradigm. The overdensities in CDM should roughly follow a Gaussian field. And so one just directly maps from here, this flux distribution, onto here, this Gaussian field. That is to say, the low absorption regions, of course, have low delta, so you would map these pixels in the spectrum to low overdensities, and you would map these pixels in the spectrum to the high overdensities. Just a simple transformation between flux and overdensity, and Gaussianize it. Okay, so good so far. Then you can, again, further visualize it here. Here's our flux spectrum from the numerical simulation. Rupert has now mapped it into overdensity, and that's being plotted down here. So where we've got strong absorption, you've got higher overdensity, very strong absorption, the highest overdensities, very little absorption, the low overdensities. Yeah. And now you can analyze this density field, which is what you're after if you're interested in measuring the power spectrum of overdensities in the universe. So that's done. You do it along one dimension first, because that's what you have in a spectrum. This delta squared term is estimated from the Fourier transform of the overdensity field, as you've just generated. And then you relate this one-dimensional power spectrum to the three-dimensional as above. The challenge really becomes propagating errors and understanding the biases and systematics in this approach. That involves extensive numerical simulations. So this really links back to how well can we simulate the Lyman alpha forest from first principles. Here's some of the earliest results on that. K is a measure of like the scale, right? Inversely proportional to the length scale here. And again, you're on scales of megaparsecs to maybe 10 megaparsecs as plotted. This is the flux power spectrum in the data. The turnoff at high K or small scales may be associated with thermal broadening in the IGM. I'll come back to that. And then this is pretty directly from the data, you then infer from that Gaussianization and the transformation from 1D to 3D, the power spectrum of the universe on these scales. And here overplotted are three estimates of what P of K should look like from different cosmological parameters. And I guess you get some constraint, in the early days at least, on the products of several of the key cosmological parameters. Degeneracy, obviously, between them, but it's a very strong and valuable constraint nevertheless. They do depend to some degree on the IGM properties, which, like the temperature, which are unknown, which I'll come to probably about now. Here's the state-of-the-art, nope, I take that back here, was the measurements from the Sloan Digital Sky Survey. If you can't read that in the back, that's the delta squared of F, so it's the flux power spectrum. And this is over a series of redshifts that one is sensitive to with Sloan, 3,000 spectra. So you can do this technique, you may apply this technique even on the lower resolution data. All right, as much as I harped on resolution, and it does, well, it's necessary for some of the experiments, like the deuterium measurement. The concept of mapping flux to overdensity applies at any resolution. There are systematics you have to worry about, and there are mappings between the two that become more important. But nevertheless, the concepts remain. You're no longer, because of the lower resolution, you're no longer sensitive to the highest K values, the smallest scales within the IGM, but nevertheless, it can be applied, and it has. And that slide's too dark, but this is the mass scale of the universe, and this is just the kind of a P of K type plot. And just to emphasize that the IGM really is unique compared to what you get from this cosmic microwave background and cluster experiments and many other cosmological experiments. So it provides a complementarity and a completely unique probe of the power spectrum. This is maybe a better description of that. Here's two constraints on sigma 8, the normalization of the power spectrum, and NS, the rolling index spectrum. Let's see, the index of the P of K. Somebody help me out. Index, the rolling index. I think that's what we would call it. WMAP alone, and then WMAP plus constraints from the Lyman alpha forest. So it's now become standard for those who work in the field of cosmology to bring in the Lyman alpha force, the IGM, as a fundamental and complementary constraint to which you can derive from CMB or type 1a supernovae or whatever other experiment that you can muster. And here's the state of the art from the Boss experiment, and constraints on a whole host of cosmological parameters from those data. The error is now entirely in the systematics and also in the modeling. Some of the systematics include the H1 absorption we've described. We are trying here, we wish to perform the experiment here, as I started, on the quasi-linear IGM, on the gas that's on the largest of scales. We wish to avoid galaxies and avoid overdense regions, so damp Lyman alpha systems in this context are a contaminant, need to be identified, removed, and dealt with. So too our metal line absorption, that's a bit of a weaker one, but you're really in, the signal noise here is so high that you're really in, well, you're sensitive to any contaminants at that level. Going the next step further in correlating the flux within Lima forest, it's now been performed on 3 dimensions. I just described to you what you can do along 1D spectrum, okay, get the power spectrum in the 1 dimension, and you can do that for many sight lines, but you don't put them, you put them together at the end, but you don't correlate them sight line to sight line. That's at the heart, that kind of concept is at the heart of the BAO experiments with the intergalactic medium. Now you're cross-correlating the flux across the sky, okay, in 3 dimensions. It required a massive survey, like BOSS. It was not capable, really was not something that could be done prior to that. And I wish to really emphasize all of the signal here lies in the noise. Intentionally, is that a fair statement? Maybe not. A little bit. Somewhat intentionally, the project took data like this of quasars in the Lima forest. So I just randomly took one of their spectra, one of their good spectra. These were cut out by K.G. Lee for his PDF analysis, which I'll show you in a few minutes. Here's the error array in red. If you can hopefully see on the back, and the black is just the signal. This is the Lyman alpha forest region. Trust me, Lyman alpha is right over here somewhere of the quasar. And that's the data that's used to infer the flux distributions across the sky. So all the experiments in the noise, which means you have to understand your noise very well. A lot of work goes into that. You need to understand how best you can estimate a continuum that doesn't bias the results. The purple here is this mean flux regulated continuum I introduced, and so on and so forth. But appreciate the signal that pops out is not one you see at all by eye in the individual spectra. That's just not, that's not the way, it's not part of the game here. Nevertheless, it's worked. Here's they mocked up model data and performed analysis on it. And then here's analysis on the real data, the real spectra. And you see at 110 megaparsecs, 1 million megaparsecs, the bump that's associated with baryonic acoustic oscillations. The IGM is not a priori the optimal tracer of baryonic acoustic oscillations, because you are probing kind of this, as I say, this quasi-linear regime, which means it's pretty unbiased regions of the universe. You prefer biased regions, they cluster more, and you get stronger signals in the BAO, for example. But at Redshift 2, it's about all you can work with. It is all you can work with, and maybe all you will work with for some foreseeable future. And it offers a completely unique regime to do the experiment and test for, well, to place constraints on models of the dark energy concept. How's my time here?
You're just on time.
Just on time.
2 seconds, maybe.
Okay. All right, now I'll pick it up here. In the evening, we'll go through a number of other constraints that we continue to get from the IGM, and I'll then finish on the future.